Hello children, what we're doing is extra sums of similarity chapter 1 geometry, okay? Extra sums of similarity. So question number 1, in the adjoining figure, can you see this figure? You have to find area of triangle ABC upon area of triangle BDC. And now what else is given in this figure? The length of AB is 6, nothing else, length of AB is 6, and length of D is 4. These two are given, okay? Length of AB is 6, length of B is 4. Nothing else. So when I look at it, children, area upon area, the question always tells us, okay, what property we have to use. Now, I think we have learned the first property in similarity chapter, which gives us about area upon area. What is that? The ratio of the areas of two triangles is equal to ratio of the product of the bases and respective heights. The second property in that itself, the ratio of the areas of two triangles having equal bases is equal to ratio of the corresponding heights. The third property was the ratio of the areas of the triangles having equal heights is equal to ratio of the corresponding bases. And fourth property in that was if the two triangles have equal bases and equal heights, the ratio of the area, then the areas of the two triangles are equal. So when I look at it, this first property, there were four statements in that first property. Now, which I have to use because I want area of triangle ABC upon area of triangle BDC. So when I look at triangle ABC, it's a right angle triangle. So AB is a height, BC is a base, I realize. And when I look at triangle BDC, you can see D is perpendicular to BC. Even this tells us BC is a base, D is a height. That means both these triangles have equal bases. So naturally, ratio of the areas of this triangle should be equal to what? Ratio of the corresponding heights. So how we go about writing this, children? Just have a look at this, okay? Area of triangle ABC upon area of triangle ABC upon area of triangle BDC directly, okay, is equal to, you can see it will be AB upon D. But what will be the reason for the DE? It should be, children, area upon, okay, it should be D. Okay, area of triangle ABC upon area of triangle BDC equals AB upon D. The reason should be what, children? Please have a look here. When we write the reason, we'll not write the reason in terms of ratio, okay? The way it's given in your book, okay? In the solved examples and all, they just say areas of two triangles having equal bases, are proportional to the corresponding heights, So here, what you see is, children, when you write the reason, we are not using the word ratio. What we use the word is a proportional. So remember, whenever we use the word proportional, ratio word should not be there. Areas of two triangles having equal bases are proportional to the corresponding heights. You got it? So you can clearly see this reason plays an important thing. If you don't write your reason, your half mark will go. So what happens? Area of triangle ABC upon area of triangle BDC will become equal to, children, what is the value of AB given to us in the picture? You can see 6. What is the value of D given to us in the picture? 4. 2 3 times and 2 2 times. So what do you get ultimately answer? Area of triangle ABC upon area of triangle BDC is equal to, what it will be, children? 3 upon 2. There's an answer for it, okay? We can expect a 2-mark sum of this type, okay? Now, such a figure is not a type of this figure is given, but this figure is not mentioned in your textbook, okay? We go to the next answer. Question number 2. If the ratio of the perimeters of two similar triangles is 3:7, find the ratio of the radius. If the ratio of the perimeters of two similar triangles is 3:7, then find the ratio of the area. ये sum और पहले sum में फर्क क्या है? In the earlier sum, there was some picture given of the triangles. Here, no picture is given, nothing. Let's just send it in words. The ratio of the areas of the perimeters of two similar triangles is 3:7. Then find the ratio of their areas. I want the ratio of the areas. There also I want a ratio of the areas. But one more big difference, that the two triangles at any cost couldn't be proved similar. Whereas here they mentioned these two triangles, when you look at it, these two triangles are similar. They're mentioning the two triangles are similar. So when they mention the triangles are similar, then we have a property learned, okay, regarding the ratio of the areas of similar triangles. Ratio of the areas of similar triangles is equal to the ratio of the square of their corresponding sides. Ratio of the areas of similar triangles is equal to the ratio of the square of their corresponding sides. Now remember, in the same property, we have lot many, like we can call different statements. The ratio of the areas of two similar triangles is equal to the ratio of their corresponding square of their corresponding medians. The next, the ratio of the areas of two similar triangles is equal to ratio of the square of the corresponding altitudes. The ratio of the areas of two similar triangles is equal to ratio of the square of their corresponding angle bisectors. The ratio of the areas of two similar triangles is also equal to ratio of the square of their corresponding perimeters. You can see here, children, again I repeat, what did I say? The theorem, what is there in our book is ratio of the areas of two similar triangles is equal to ratio of the square of the corresponding sides. But I told you the same property I can interpret in a little different ways. The ratio of the areas of two similar triangles is equal to ratio of the square of their corresponding altitudes. The ratio of the areas of two similar triangles is equal to ratio of the square of their corresponding median. The ratio of the areas of two similar triangles is equal to ratio of the square of their corresponding angle bisectors. The ratio of the areas of two similar triangles is equal to ratio of the square of their corresponding perimeter. So when we hear in this question perimeter is word is used, so I think I'm going to use the last statement, okay? So how am I going to do? So first thing I'm going to write, let A1, A2 and P1, P2 represent the areas and perimeters of two similar triangles respectively. Okay. Now this after this, I can say what is given. The ratio of the perimeters of two similar triangles is 3:7. So P1 upon P2 is 3/7 is given. And they want me to find the ratio of the areas of the ratio of the areas. I want A1 upon A2. The last statement, what did I say was A1 upon A2 equals P1 squared upon P2 squared. Got it? Ratio of the areas of two similar triangles is equal to ratio of the square of their squares of their corresponding sides, okay? Corresponding sides. But here, in place of sides, what will come to? Perimeter, corresponding perimeters. So what will be the answer here? Therefore, A1 upon A2 equals we don't know how much is P1, how much is P2, but we know P1 upon P2. So purposely, I'm going to write this extra step, P1 upon P2, the whole square, okay? After writing this, now I'm going to substitute. Therefore, A1 upon A2 equals, what will happen, children? You can clearly see, children. Here, I'm going to continue to the right hand side. You can see now A1 upon A2 equal, therefore, A1 upon A2 equal, you know the value of P1 upon P2, how much it is? 3 upon 7. So 3 upon 7, the whole square. So what I get? A1 upon A2 equal 9 upon 4, okay? So what is the ratio of the areas? 9 is to, 3 is to 7, so 9 upon 49. Got it? So what will be, children? If a ratio of the areas, answer equal 9 is to 49. 9 is to 49. 9 is to 49. Okay? 9 is to 49. This is the answer. Okay, children? Now, we move on to the next sum. Question number 3, children. Triangle ABC is an isosceles triangle. Triangle ABC is an isosceles triangle. Isosceles triangle means the two sides are always equal. So which are the two sides equal dimension? AB equal BC. Okay, AB equal BC. That means the base angles, angle BAC equal angle BCA should come to your mind. Okay, whether you use it or not, it should come to your mind. In an base angle, the isosceles triangle are always equal. Okay, then children, BD is perpendicular to AC. Then CE is perpendicular to AB. Now, what they wanted to prove? They wanted to prove AE into BD. When you look at it, AE into BD, which is AE here, you can see, children. AE is the segment AE. Okay, you can see segment AE here. This segment AE, you have to prove AE into BD, AE into BD, AE into BD, A and BD. They cannot be the sides of the same triangle. Tell me AE एक triangle करेगा, BD दूसरा triangle करेगा. वैसे ही बेटा AE into BD equal EC. EC को देखो बेटा किधर है? EC is this height. EC into CD. So clearly you can easily see the two triangles, children. A triangle, I'll tell you where CEA, I'll take it. Got it? And other triangle, I'm going to take it as BDC. These two triangles, I'm going to select. Why did the idea come to me at all? This, I have to select the triangle. I repeat the whole thing, children. Please keep it in your mind. AE into BD. See, this should be the last line of the proof. AE into BD. AE into BD equal, children, what it should be? EC into CD. This should be the last line of the proof. Okay, that means the second last line must have been a ratio. Second last line must have been a ratio of the segments. Ratio of the segments. Second last line must have been a ratio of the segments. If the second last line is a ratio of the segments, children, then remember how to get the ratio of the segments equal. There is only one way. You have to prove two triangles similar, children. Because when the triangles are similar, the corresponding sides are in proportion. Ratio of the corresponding sides are equal, I can say. So the question is how to select the triangle. So when I look here, the segments AE into BD, can you see AE? This AE into BD, this AE into BD, AE into BD. You can see the two segments, one is AE, one is BD. Should be equal to, you want it as EC. Can you see this EC into CD? EC into CD. The four segments, when you concentrate properly, children, you realize, got it? The two triangles you have to select. One will be like AE should be a side. AE should be a side of this triangle AEC. Got it? And the other one, CD, should be a side. CD is a side of triangle CBD. So when you look at these two triangles, children, if I can prove them similar, I think I can easily get the ratio of the corresponding sides. So let's have a look at this triangle, children. When you look at these triangles carefully, got it? When you look at these triangles, you can clearly see, children, how we go about. This triangle, ABC is an isosceles triangle first. Whenever, children, two sides of a triangle are equal. These two sides are equal. So this non-equal side is called a base. The base angles are equal. So this big triangle BAC, when you look at this big triangle BAC, okay, there are two sides equal, BA equal BC. You can see here, AB equal BC, okay. So naturally, angle A should be equal to angle C. That means this is the angle A and this is the angle C. A belongs to triangle CEA and C belongs to triangle BDC. So look at this triangle CEA and BDC. CEA and BDC in triangle, in triangle CEA and triangle BDC. You can clearly see angle A is equal to angle C, children. You can also see angle CA is equal to angle BDC, which is 90. So both the triangles are similar by 8. And once the triangles are similar, the corresponding sides are in proportion. We can get the ratios equal. And then when you cross multiply, you'll get your answer. You'll get your answer. So very simple sum, children. Very easy sum. Okay, once again, I'll repeat. Children, please have a look here. The last line should be A into BD equal EC into CD. So that should be the last line for proof A into BD equal EC into CD. So from here, we realize the second last line must have been a ratio involving these 4 segments. तो वही क्रॉस मल्टीप्लाई करने का भी आंसर है ये ratios equal दिखाने का टेक्निक है you have to prove the triangle similar so just identify the triangles okay with the segments only I'll identify the triangle flying AE segment you can see here AE segment okay where is AE segment you can see children in the picture AE segment is here AE segment is here then children we want A into BD, A into BD. When I look at BD, children, where is BD segment? BD is this, children, this green segment. Now, why did I show you to the different colors? Okay, but the simple reason is simple. You can see them. They cannot be the sides of the same triangle, A and BD. 4 letters, A, E, B, D. Triangle का नाम तो 3 letter रहता है. तो ये दोनों एक ही triangle के हो नहीं सकते. Then children, when you look at it, equal EC. What is EC, children? You can see EC is here, children. EC is here. This is EC. Oh, this is giving one triangle now. You can clearly see. EC and A, they belong to the same triangle. So I get this triangle. What is this triangle, children? What is the name of this triangle? You can see here, children. This triangle is CEA. This triangle is CEA. We can see again, children, BD. BD and BD goes to EC into CD. So just have a look at CD, children. CD. CD is here. CD is here, children. You can clearly see CD is here. Okay. So this CD, when I go for CD, I can mark CD here, green color, and it becomes the side of this triangle, green triangle, okay, BDC. So you can now clearly see the 2 triangles, children. These 2 triangles, we have to prove them similar. Which are the 2 triangles? One, this triangle CFA, and the other one is triangle BDC. Triangle CEA and triangle BDC. Triangle CEA and triangle BDC. You can clearly see one pair of angles are congruent. Angle CEA, congruent angle BDC, I can say each is 90. But where is the other pair? Other pair is, you can clearly, the other pair of angles. ABC is an isosceles triangle. So when I go for this isosceles triangle proof, you can clearly see, I look at this triangle ABC first. In triangle ABC, what I realize, AB equal BC is given to us. So whenever 2 sides of a triangle are equal, the angles opposite to them are equal. Therefore, angle A congruent, can I say angle C? I call it as 1 by isosceles triangle theorem. Now, why did I name it? I numbered it, isosceles triangle theorem. I numbered it because I can use it now. So look here, in triangle CEA, in triangle CEA and triangle 1-to-1 correspondence CEA, so it should be BDC and triangle BDC. Angle CEA congruent angle BDC, each is 90 degrees. Then you can see, children, angle A of this triangle E is congruent to angle C of this triangle, I can see this from 1. Therefore, triangle CEA is similar to triangle BDC by AE test. And once the triangles are similar, the corresponding sides are in proportion. So you can clearly see your EC, or I can EC upon BD equal AE upon CD, corresponding side, the sides, the segment sides which are involved, I write only their names, I need not write the third ratio. Corresponding sides of similar triangles. Corresponding sides of similar triangles. Therefore, when I cross multiply AE into BD equal EC into CD, correct, you get the answer. So very simple sum, children. I don't think the sum is difficult. Okay, we go to the next sum, children. Let's try to draw the figure for it in a right angle triangle ABC. Okay, right angle triangle ABC. So when you look at right angle triangle ABC, I don't know which angle is 90. So I'm not marking which, I'm not naming it immediately. Okay. But when I read it further, in a right angle triangle ABC, the perpendicular drawn from point C on the hypotenuse. And from point C, the perpendicular is drawn on the hypotenuse. C has to be the vertex. If C has to be the vertex of this triangle, and you have to draw perpendicular on the hypotenuse, that means C should be 90 degrees. C should be 90-degree angle. C should be 90-degree angle. Then only I can draw perpendicular to the hypotenuse from here. Got it? Then only I can draw perpendicular from C to the AB. So what I do, I just draw that perpendicular. Okay? CD perpendicular to hypotenuse. CD is perpendicular to, you can say, hypotenuse AB. CD is perpendicular, 90-degree marking, okay? Then children, further, the bisector of angle C meets the hypotenuse at E. Oh, the bisector of this angle is also drawn of angle C. The bisector of angle C, some like here, suppose, okay? This is a bisector, doesn't look like, but please assume it as bisector, okay? The bisector of angle C meets the hypotenuse at E. Now, AD upon DB, can you see this ratio of the segment AD upon DB? Is equal to AE square upon EB square. Okay, the ratio of the segment AD upon DB. Please look at AD and DB. Is equal to AE square upon EB square. So, can you think of getting a method, of getting AD upon DB? So remember, children, whenever you see a right angle triangle, I'll just tell you, whenever you see a right angle triangle, children, and in that, if a perpendicular is drawn from the vertex of the right angle to the hypotenuse, you see a perpendicular is drawn like this. When a perpendicular is drawn from the vertex of the, please have a look here, right angle, just rough diagram I'm drawing, I'm going to rub it off, that's right. In this triangle ABC, angle B is 90, and BD is perpendicular to AC. So what happens, there are three triangles formed. One is a big triangle ABC and two small right angle triangles. You should know all these three triangles are similar by a theorem called similarity in right triangles. All the three triangles formed are similar. So naturally, when I say AD and DB, if I want these ratios, I get an idea. I see a big right angle triangle ACB, okay, in which I can clearly see the angle C is 90 degrees. So naturally, I get an idea. All the three triangles are similar, children. If all the three triangles are similar, so in one of these triangles, ADB and CDB, if I take these two triangles, ADB and CDB, I can get that AD upon DB. So just think about getting this AD upon DB. How to get this AD upon DB? How to get this AD upon DB? So what I do, I use the similarity of right angle triangle theorem. See how we use the similarity of right angle triangle theorem. See, in triangle, ACB, first the name of the triangle. Then a 90-degree angle. Angle ACB equal 90 degree. What's the reason, children, given? So naturally, children, therefore, I can say that and segment CD is perpendicular to hypotenuse AB. So naturally, all the three triangles, triangle ACB, big triangle, am I right? ACB, similar triangle ADC, ADC, similar triangle CDB by similarity in, this is figure number 1, by similarity in right angle triangles. I got AD upon, now you can see actually, where can I get AD and CD? With AD and BD, you can see here. So AD upon CD equal AD upon CD equal CD upon BD equal, okay, is equal to AC upon BC. Corresponding sides of similar triangles. Corresponding sides of similar triangles. Okay? Then, children, you can see here, children, this is what a reason for it. Corresponding sides of similar triangles. Corresponding sides of similar triangles. So you got this ratios equal. You can see here, you wanted AD, you got AD, but DB you wanted, DB you got it in the second ratio. Doesn't matter, children. I'll have to use common sense to get it like this. Okay. Then how to get this AE and EB? So again, children, in triangle ACB, what do you see? Ray C is an angle bisector. Is an angle bisector. Angle bisector of angle ACB is given to you, children. Okay. So now whenever you see an angle bisector, children, we should can use property of angle bisector. So AE upon EB equal, what it will be? AE upon EB, property of angle bisector. AE upon EB equal AC upon BC. AC upon BC. Correct? Reason, property of angle bisector of a triangle. By property of angle bisector of a triangle. By property of angle bisector of a triangle, children. Bisector of a triangle. Now you can see here, children. In this this is statement number 2 and this is my statement number 3. Now when I look at 2 and 3, the right hand side, can you see on ratio AC upon BC? I got it here. Even in this, I got AC upon BC. Got it? So can you see, children? Can I say one of this AD upon CD? Therefore, AD upon CD is equal to what I can say AE upon EB. Okay, can I say like this statement number 4 from 1 and from 2 and 3? And also, children, why I get this AD upon CD is also CD upon, like this CD upon BD is also equal to CD upon BD is also equal to, children, AE upon EB. Statement number 5. And now you can check, children, what happened. I wanted AE square upon EB square. Hey, if I multiply this, right, this two statement number 4 and 5, the right hand side, if they get multiplied, AE square upon EB square I can get. And look, left hand side when they get multiplied, AD upon CD equals into CD upon B. Oh, CD can get cancelled and you can get your answer. So what I do now, multiplying 4 and 6. And when I multiply 4 and 6, I'm going to write it here, children. I don't have place, but I'm just going to squeeze in here. Okay, I'm going to multiply here, children. So when I multiply, you can check it here. What will happen, children? The left-hand side will get multiplied. Okay, when the left-hand side gets multiplied, what will happen, children? Okay, it will become AD upon CD multiplied by CD upon BD, and here AE upon AB into AE upon EB, it will become AE square upon EB square. And now when I look here, children, this CD and CD will get cancelled. So ultimately you get AD upon BD is equal to AE square upon EB square, children. So I think people have understood it.